and welcome to another Triangular Talks session. My name is Shreya Kalyan, and I'm the CEO of Agora Mathserv. Triangular Talks is a forum for students to interact with and hear directly from industry executives across various companies and organizations about how they use STEM concepts and problem-solving skills in their day-to-day work lives. This will be a series of 1-hour online Zoom sessions consisting of 3 parts: an introduction, a presentation, and a Q&A session. These talks will revolve around one central idea: the triangular method of solving problems. This method begins with a problem. From that, one gets innovation, which one will finally use to solve the problem. To help students connect the dots between classes and real life, speakers will be asked what they do every day and how they apply their knowledge of STEM and problem solving. This will introduce students to different industries and motivate them to nurture their problem-solving skills and not give up. The most common question asked by students in any math class, especially mine, is, why are we learning this? Or when will we ever use this? This program will answer these questions and encourage students to take the initiative to learn and do more. Before I introduce our speaker, I'd like to thank Ms. Madhangi Shivaramakrishnan, Mr. Andrew Zhu, and Mrs. Lisa Go for making this possible. Now on to our speaker. To talk about the challenges of deep water oil and gas and subsea riser designs, we have Dr. Fengjie Yin. She received a bachelor's degree from Tsinghua University in Beijing, China, and a PhD from the University of Toledo, both in mechanical engineering. She is a principal engineer and project manager at 2H Offshore. She has over 15 years of experience in deep water subsea engineering and is responsible for engineering technical management over a range of subsea riser engineering design and integrity management projects. In addition, Dr. Yin is a subject matter expert for engineering critical assessment and fitness for service assessment. She has been a committee member of the American Society of Metals for 10 years and is in charge of student affairs. With that, I would like to give the floor to Dr. Yin.
Thanks a lot, Shreka, for the introduction. And here I will try to share my screen. Okay. Can you confirm? Can see the full screen of my presentation slide?
Yes.
Okay, great. The agenda of my presentation today. First of all, I will give a little bit more introduction of myself, and a brief introduction of offshore oil and gas industry and the history of offshore development. Also, particular focusing on riser design, subsea riser design in deep water offshore oil and gas industry. And overview of engineering challenges associated with subsea riser design, also particular focus on deep water oil and gas industry. With this topic of this organization is to help the students to apply what they learned in the classroom to the real life industry. I have here, in the end, I'm going to give 2 case studies. First is the fitness for service evaluation based on inspection data. And the second is a riser integrity management program using monitoring data to see how this really applies in real projects during the project processing and the problem solving, problem identification, and giving solutions. Okay. A brief introduction about me. I got both my bachelor and the PhD degree in mechanical engineering, and I've been working for more than 15 years in the oil and gas industry. Currently, I'm working in 2H Offshore as a principal engineer and project manager. I've been managing over a range of subsea riser engineering, design, and integrity management projects over the world, including Gulf of Mexico, South America, West Africa, North Sea, in Europe, etc. And the projects cover consulting, design service for various operators, including Exxon, BP, Chevron, Shell, Equinor, Lorac, and Murphy, etc. prior to that, I have been working closely in automotive industry, conducted my fatigue testing in fatigue and fracture lab in Ford Motor Company, and also fatigue testing and modeling for American Iron and Steel Institute. Currently, I have been serving for the committee member for ASM Student Affairs since 2012, being judged for the Houston Science Fair, and also responsible for evaluating and awarding scholarship for qualified college students in the engineering field. Brief introduction of the offshore oil and gas industry. As you know, hydrocarbons have been extracted from subsea reservoirs for many, many decades. Just one thing I forgot to mention, if you have any question, please don't hesitate to interrupting. You can ask a question at any time during my presentation. You're welcome to do that. Okay, continue the introduction. Offshore production is moving into ever deeper water, more than 3,000 meters, and even harsher environment. What is a riser? A riser is a pipeline which rises through the water, which transport the fluids or equipment between the seabed and the surface of either fixed floaters, fixed platform or floaters on the surface. There are many complex engineering challenges must be safely overcome. So it is a global industry with various disciplines which could provide support, including mechanical, material, control system, structure, data science, statistics, computer science, and artificial intelligence. Talking about the offshore oil and gas industry, people may or may not have seen some of the offshore platforms. You can see some of the offshore platforms pictures on the left side, but I'm pretty sure everybody has used the end product of the offshore oil and gas to get gas from a gas station. Starting of the beginning of the project, usually the offshore sectors is divided into blocks. This is an example of the blocks, how the blocks is divided in the Gulf of Mexico. First, the government sell exploration licenses or lease to the oil companies, or we call operators. Then the oil company is required to shoot seismic surveys or drill exploration wells within an agreed time frame. And if oil and gas is discovered, the oil companies will form partnerships to undertake development normally. And you can see the different blocks divided in the Gulf of Mexico area, and the blue areas, blue dots are the different platforms in this area. You can see lots of development in the Gulf of Mexico area. Talking about the basic reservoir geology, although this is not one of my expertise, or give a very brief introduction, because this is a very first piece of the jigsaw or the puzzle. The hydrocarbons are found in reservoirs beneath the seabed. It may be some distance below the seabed, and it may spread all across a large area. And so first of all, the seismic analysis needs to be conducted to identify potential locations which may have oil and gas findings. So in this analysis, lots of math go into it. It can be complex structure extending over many, many miles. And currently there are directional drilling. The wells are drilled all around the corners and even horizontally as well. the history of the offshore industry. At first, in the very beginning, the offshore wells first drilled in shallow water in Gulf of Mexico, and using fixed platforms, and because at the time it's all shallow water. And the technology has been extended to the North Sea in the 1970s and all around the world later. And when the water depth is beyond 300 meters, fixed structures are not practical anymore. So then the floating systems are introduced. There are various types of floating systems listed in the picture below. Again, a little more about what is riser, what is the day-to-day life I'm working with and in designing. And the subsea riser is a pipeline that connects a well at the seabed to a vessel or platform at the surface. Now with the offshore wells be found in locations with deeper water depths, including water depths of up to 3,000 meters in very severe weather condition, including wind, the ocean currents, and the wave heights can be as high as 20 meters. And the riser must be able to safely withstand all sorts of complex dynamic loading over the life of the field, as long as the field is still producing. There are normally two stages of developing a subsea reservoir. First is exploration to find oil and gas, and the second is production. Exploration, in the exploration stage, normally it requires the drilling of the wells below the seabed, and typically using an existing drilling risers. And me, myself, is more focusing on the production riser systems, which are typically specifically designed for the specific site to achieve continuous production for a service life, for example, 20, 30 years or even longer, etc. There are different types of risers in these two different stages. In the drilling exploration stages, we call it drilling riser. And in the production stage, we have production, export, and service risers with different, divided by different function. And to connect to a different surface facility of floaters, there are the regular boat shape like floater, call it the FPSO, and there are other types of floater, TLP, semi-submersible, and spar, with different purposes selected for the specific site. And there are also different types of production riser systems. One on the left side, the top tension riser, and steel catenary riser or flexible catenary riser. The shape is, you can see the shape of the riser is a catenary shape. And nowadays, a steel lazy wave shape or a flexible lazy wave riser is used more and more. There are buoyancy put in the middle section of the riser, which is installed or designed to mitigate the motion transferred from the floater to the touchdown point of the riser, which is touching the seabed, to help perform better strength and fatigue performances. And there are other type of risers, which we call it hybrid riser. It's a hybrid combination of the top tension steel part with buoyancy can put in the middle, and with a flexible line connecting to the floater. There are various material selections corresponding to different connections. When we choose high strength steel with then we'll normally use a threaded and coupled connection because welding is not that easy. And there are welded connections, and there are materials we call it a flexible pipe with a combination of layers of steel and composite to serve for different purposes. There are lots of design challenges in the riser system. First of all, the big chunk of riser pipe will result in significant weight putting on the whole system. And it's a slender structure, unsupported structure, which is vulnerable to buckling. And there are also complex dynamic loading, including the environment exposed to wind, wave, and current from mid-ocean data. And the motion of the surface vessel is transferred to the whole system, which may result in high extreme stress and also cyclic loading, resulting fatigue damage. Probably if you may not know about what is fatigue, because fatigue is actually a big concern in the riser design. Easy to explain what is the fatigue. If you put a piece of wire, like a metal wire, and you bend it back and forth, this will result in fatigue damage instead of like overstress. After a few times, you may see this wire failed because of fatigue damage. And there are other challenges listed here because of the reservoir production fluid has a high temperature, high pressure, and the flow assurance issues, and also including marine growth issues and material and fabrication selections. And because it's exposed to seawater, the corrosion might be very key part to be considered in your design. Even the production fluid may be resulting in a corrosive environment. And installation is not easy, and also you have to make sure the whole system is designed life over 20 or 30 years or even longer. There are also some unexpected creatures, which I'm going to show in some of my later slides, which are not designed for. The key drivers of the riser design, first of all, is the strength behavior. Second is the fatigue behavior, because it needs to withstand the design life of 20 to 30 years, as I mentioned. The fatigue sources may include wave motion and vortex-induced vibration, or in the vessel-induced motion and slugging, and installation resulted fatigue damage. Another key driver or needs to be taken into account is clashing or interference, which needs to be considered the riser with clashing with the adjacent riser structure, and clashing or interference with the adjacent hull structure or vessel structure. What is vortex-induced vibration? In riser design, you may not be familiar with it, but it is basically a slender pipe structure. If you observe carefully the antenna of the car during strong wind, when the strong wind is blowing the antenna will vibrate perpendicular to the wind direction. So sometimes after this, maybe you pay more attention to the car antenna, you probably will see notice the vortex-induced vibration. And this kind of vibration is a key fatigue damage source in the riser system. This is a video capture the vortex induced vibration of the pipe. You can see the motion captured during a strong loop current event in the right conductor pipe system. And as I mentioned, another key part of the design, normally analysis, we do simulation to check, make sure the riser doesn't interfere or clash with the adjacent structure, including other riser or the whole system riser pipes. You can see in extreme event or environment condition, the riser pipe is moving closer to the adjacent structure, and the analysis simulation is conducted to find out what is the minimum clearance between these two structures and make sure normally design not clash with each other. And if in any case it's designed during design, it is clashing during a very extreme event, like a 100-year current event or 100-year hurricane event. If it's allowed to clash, we need to calculate the clashing energy to make sure the clashing energy is below the allowable. Here there are some actually, I think it's some cool videos. You see, you can capture the in the camera in the whole riser system. Here, I don't know what is this in the water. And can you see this is a big, huge
whale?
whale. Yeah, it is a whale, right?
And I think that in that video,
Yeah.
I think it's a jellyfish.
Oh, is it? Oh, okay, cool, nice. So it's good to identify. I don't know. Yeah. So these creatures are approaching the system. We don't
Actually, that's a ray.
That's all right. Okay. And we actually have experienced the whale biting one of the control lines, which they may think it's some food. These are really unexpected things we didn't design for.
I also see some aquatic fouling, like mussels.
Oh, cool, yeah. Okay. Moving on to the I would say exciting part. For me, it's an exciting part. How we apply this to problem solving. First of all, I will give an overview of the design cycle and the application of two different types of measured data, including inspection data and the monitoring data. Monitoring data includes the meta-ocean, monitoring wind, wave, current, and the strain and the motion sensors, giving the data, and how this is applied into solve the design problems. This is kind of a busy figure, but let me go through with you step by step. This is mainly what we do to fulfill the whole design cycle. Of course, like lots of design work is done in the beginning of this to get to a as-built design, including different vessel type selection, different riser type selection, different material selection, and different shape, and also conduct lots of analysis to make sure you have a robust design before you confirm this as-built design. But after the as-built design and after the installation, continuous inspection and monitoring normally goes in service while the whole system is in service. And the inspection or monitoring data include the general visual inspection and the cathodic protection inspection and the inline inspection during the service. In many times, monitoring sensors are installed in the system to monitor the environment data, monitor the strain and the stress data. With all these, an additional system analysis will be conducted, including the fatigue analysis, or we call it the ECA, or fitness for service engineering critical assessment, including soil data, meta-ocean data, and vessel motion data with different softwares to analyze the whole system while it is in service, because things might change during the service compared to the design phase. After that, and conclusions needs to be made to see if you have to modify the system, including replace some of the critical components or repair the coating or clean the vortex-induced vibration suppression device, including, for example, we call it strakes to mitigate the vortex-induced vibration-induced fatigue. And if these modifications are applied, then the update will be analyzed again, which will feed into the system analysis again to reconduct the whole system analysis to check if you have still have the design life is met, or if you can extend it for a longer time life. We call it a life extension assessment. So this is basically how the whole system design cycle is working. So the first case study I put here is a fitness for service evaluation based on inspection data during the service life. First, how the problem is identified, because during the service, some inline inspection has been conducted to the infield lines, risers, and pipelines. And the inspection report or inspection results identified the various flaws all along this whole system. So yeah, after evaluate all these inspection results, decision has been made. We need to conduct an assessment to evaluate whether the whole system is continuously fit for service, if it can still be in service, or if you have to shut down the production. This is a typical inspection result picture through different types of non-destructive testing, including ultrasonic testing, or some through inline inspection through peaking sensors, all through the whole pipe system, and to measure at all 360 degrees of the pipe and all along the pipeline system, the riser system to see if there are significant wall thickness loss, wall loss in different areas. And the red dots are identified as a critical wall loss. Basically, it's the wall thickness measurement you just for the whole pipe. It's one small section of the pipe. And once we got this inspection report, we would normally conduct a detailed processing procedure of the whole measurement of the wall thickness, and to identify a key location where it has a larger wall loss, or where it's compared to the nominal designed wall thickness of the pipe. However, this is not the only input in the criticality of the whole system of all along the riser and all along the whole circumference, because the wall loss may be severe in some part of the structure which the stress is not as high, or the strain and stress is not as high. And material wise, if it's at a weld location instead of a parent metal location, it's more critical. So it's basically a combination of location and the material type, whether the weld or base metal, and also the stress distribution all along this whole system. We come up with a criticality index calculation. And after, so this is a typical stress distribution in our analysis. At the different, you can see the y-axis is the stress, and the x-axis is the distance from the hang-off location of the riser. And you can see higher stresses at the hang-off location, higher stresses at the touchdown point where the riser touches the seabed. So these are the key locations. Combined with the measured inspection data, coming up with the different criticality of these anomaly features of the flaws. So since there are tens of thousands of features identified, we have to identify the most critical one. After this screening analysis, by calculating the criticality index, the most critical flaws at the most critical locations, which is with the highest criticality index factor, have been identified. And for those most critical flaws, we will conduct a detailed fitness for service assessment. The objective is to make sure the whole system still has the acceptable fracture strength, and by conducting crack growth analysis, we'll make sure the minimum fatigue life is adequate to last till the end of the design life. So by conducting these assessment combined with the inspection data, we confirm the whole system still can last till end of the design life. So we can still use this system to produce or continue produce oil and gas. Okay. There are a second case study put here. In this project, we put on lots of monitoring sensors. It's part of the integrity management program, and the sensors are put on a riser system, which is a steel catenary riser system. Why in the beginning it's decided to use these sensors to be applied to continuous monitor the whole system? Because at the time, this is a kind of new system design, and was big concern of fatigue and buckling of the riser. This is a kind of a little bit of exaggeration of the riser system. In a very extreme event, you can see the movement of the simulation, the movement during an extreme storm, and you see buckle has been identified in this area. And because this is it's been a big concern, and the whole monitoring system is applied to the Tahiti infield risers at various locations. Like I explained, the hangoff location where the riser is connected to the vessel and the touchdown point are the main major concern of locations which has higher stress distribution. The objective of installing this monitoring system, first of all, is to understand the fundamentals, to help designers to have confidence in your design, to understand the fundamentals, including the riser vortex-induced vibration and Hall-induced riser response and the riser to soil interaction, to support the design validation and also support the whole system integrity management program. In the monitoring system installed, including 5 motion sensors in the near the hangoff location and 2 strain sensors. And in the touchdown zone, close to the touchdown area, there are 5 motion sensors and 11 strain sensors installed. And the whole monitoring system is what we call a real-time monitoring. So the measured data is transferred real-time to the vessel, to the floater, again transferred to onshore simulation lab. So you can conduct a real-time calculation to make sure there is no catastrophic event causing damage of the whole system, and keep feeding into compare with the key performance indicator if there is a orange alert or red alert for the whole system. And you can see the wires here is for transferring the monitoring data, and these structures is what we call what we call a strake to help mitigate the vortex-induced vibration of the whole riser system. And the monitoring data helps to identify if this suppression system is working well or not. If you have something become loose during installation, or you lose some of the strakes during the service, it could easily be identified by analyzing these the measured data. And this is also for the top side, the data acquisition system to help to compare together. This is one of the results from the fatigue tracking, as I said. While you measure the real-time measurement of the stress and strain in the whole system, in the lab, there will be simulation conducted in real time, and to calculate at all different locations, all the critical locations, continue calculate the fatigue damage by calculating the fatigue damage accumulation overall at all locations against different limit, amber limit and the red limit. when it's approaching this limit, a warning will be sent out and decision needs to be made. So you can see these in this system, it's far away from the design limit. So it kind of confirms the design is robust and it can continue in service. Another key finding from using the monitoring system is by calculating the riser response from the monitoring data, which is the red dot, and also by monitoring the current speed in real life, in real time. You can see there's not much correlation between this riser response and the current. You can see in high current, the riser response is not extremely high. And this lack of correlation actually proves the strike or the VIV suppression system is working well, is performing as expected. If you see like in high current, the riser response like is shooting up, it means you need to check you may be losing some of the VIV suppression streaks and might need to reinstall these during service. So overall, for these problem solving, and the conclusion of this project is the measurement is conducted to provide feedback to confirm the riser integrity, the whole system integrity. And the analysis of this riser response show all the measured parameters are below any concern limit, which is validating the whole riser design process. And again, the measured data and the calculation is a very critical input for life extension. For example, if the whole system in the beginning is designed for 20 years, and after 20 years, it's the whole field is still producing, and you would like to extend the life as long as it's still producing, the additional analysis assessment needs to be done. And what can be a good support in the critical calculation is the measured data. If nothing is changed, you would say the whole system is designed for 20 years. How would I be able to extend longer life? The answer is the measured data. As long as you have the measured data available, if the measured data is confirmed to have less riser strength and fatigue response, that is a good indication of the whole system can be extended to even longer life. Okay, I think this is the end of my presentation. Thanks again, everybody, for listening to my presentation. And if there are questions, I'm opening for questions at this time. Thanks a lot.
So Dr. Yin, there is a question in chat, and you may have addressed this through your presentation, but I will read it out again. How do these floaters last? If they last long, what is an approximate of how many years it would last until you have to change one?
To what last?
The floaters.
Oh, the floaters, yeah.
Right.
The floaters is also designed, so the whole system needs to be designed consistently. So if your riser system is designed for 20 years, then the floaters also needs to be designed for 20 years. So it's a consistent whole system design. And if even for life extension, if you want to extend it for longer life, the floaters needs to be assessed again to make sure it will meet the extended life. So it's the whole system needs to be consistent. It's not like you check the riser system can last longer and the floater doesn't last that long. Then your design life will be the shorter of these two system. Yes.
Thank you.
Jason?
So do you build a prototype before you actually build the real thing?
Yeah, we sometimes use 3D printing to print some of the prototype in like demonstration, and also we will conduct some model test in like a water tank. For example, we have testing lab in Texas A&M University, and also in Shanghai. There's a newly built testing lab for the deep water riser system to check if like a vortex induced vibration is as predicted, as high as predicted. Sometimes we conduct the real size test or a scaled to make it a smaller scaled back to a smaller size test. Yes, we do have prototypes on different scales in testing. Thank you. Any more additional questions?
So what's the best shape for a riser?
Yeah, so there are different types of shape we could select for different vessel type, right? There is no exact answer for which type would be the best. For example, we could select catenary shape, and if your vessel is not directly on top of the drill center, and if the vessel design is directly on top of the drill center, you could use the top tension, the straight riser system. And if your calculation shows there is a very severe fatigue damage due to the environment, harsh environment, probably you would select a lazy wave shape, like putting on, like what I showed, putting on buoyancy module in between, in the middle, so it kind of mitigate the transfer of the motion of the vessel, floating vessel, to the riser key touchdown point. So more consideration needs to be taken into account in selection of the shape. Yeah, that's a very, very good question. And also not only in design, we have to also consider the installation capability in that area, and the adjacent infrastructure in the adjacent area. For example, in the Gulf of Mexico, the infrastructure is very mature. There are lots of pipelines, platforms already developed, and lots of data available. But in other areas, which is not like West Africa, is not as mature as this area, and the local infrastructure is not as good. Different selection, different type may be selected. Once you produce oil, you probably it's hard to directly transport to onshore, and the economic cost needs also to be taken into account. If your reservoir is producing good quality and very huge amount of prediction of the oil and gas, and you probably could afford a more expensive system, then you can have more challenging design. But if the whole system you cannot afford a very expensive system, then a cheaper one may be selected. So, and also like lead time, if you need different connections, if the whole component needs to be waited for a long time, and if the vendors only limited vendors are available for that, then you need to also reconsider it whether you want to select that. That's a very good question.
A couple more questions on chat, Dr. Yin. Thank you for addressing that. Do you have to let other big vessels in the area know where your equipment is so they don't come in contact with any of it or damage it?
Yes. So like I said, because the government controls the lease, so the operators will work with each other to make sure they won't interfere with each other while working on the adjacent area. And normally one field identified if you are going to lease that block, and 2 or 3 or 4 more operators will work together at different shells. Like for example, Exxon will have 40% of shell, and then BP will have 30% of the shell of this field, and they will work together for this particular field. And for the adjacent blocks which belong to another operator, they will know not to interfere with each other for the adjacent field. So this is there are different government groups to make sure of that, no interference with each other. Yeah.
Thank you. There is also a question about, obviously Yashaswini is very impressed with your presentation. She wants to know which university you went to learn all of these. So maybe you can give the audience a little bit more background about how you got interested in this and how you got involved. I know you did that in your introduction, but
yeah.
More detail, that'd be great.
Actually, how let me see, probably I would directly, not showing my introduction page, I would directly talk about it. So how I got interested in the mechanical engineering area is when I was in high school, my father always took me to his office, and he is a geologist. He used to be a geologist, and later on he kind of converted his career to be a design engineer. So he has both background of a geologist and engineering background. So in his office, this was the first time I was exposed to the engineering field. And then in the college entrance examination, we have to select what major you want to be in. And at that time, I thought engineering. I really want to go for the engineering field. And actually, without knowing exactly what is the mechanical engineering, what is that in the daily work, what is about. So it is a good opportunity, like if at a high school time or even earlier time, you are exposed to different industry to see what is really people work day to day. It's instead of like imagining what it's about. That's why I select my major in mechanical engineering, and started to learn all the solid mechanics, fluid mechanics, material science, and in Tsinghua University in Beijing, which is one of the top engineering school in Beijing. And after that, I decided I want to pursue a higher degree and apply for scholarship to come to the US to continue my graduate study, continuing in mechanical engineering. But at that time, the industry I worked closely with during my PhD time was the automotive industry, and looking a lot into fatigue issues for the automotive components, different automotive components. And when I graduated, got my PhD degree, the automotive industry actually was not in a booming shape. It was kind of going flat. That's why at that time I switched into oil and gas. In 2006, the oil and gas industry was booming, and also there is lots of increased requirement in that industry with engineering background, and I was really exciting to know like what I learned in automobile industry. In metal fatigue is well applied in the oil industry in this because the dynamic system caused lots of issues, including strength response and fatigue response. So basically, the whole idea of engineering background, I think it's all connected. So what do you need to learn the basics well at first, and it could easily be applied into different industries. But it's a good time to be exposed to know what is different industry has been doing to apply this knowledge. Thanks.
Wonderful, thank you. And where are the most risers?
Where are the most
risers or the platforms? Like which parts of the world?
Which part of the world? Yeah. So like what I said, a lot in the North Sea area in Europe, and a huge amount in the Gulf of Mexico, near Texas, Louisiana area, and recently lots of development in Brazil as well, and also in South America. Like currently I've been working several key projects with ExxonMobil for the new findings. If you Google to type the word Guyana country, in the Guyana field, lots of findings in that field recently as well. And in West Africa, so the deep water riser and platforms right now, it's distributed everywhere, I would say. In Gulf of Mexico, it's huge amount of deep water riser systems, I would say.
Thank you. Yashaswini, do you want to expand on your question? You feel free to come off mute and share your question about how it was made. Did you want to expand on that?
Yeah, I actually don't understand how the riser was actually made. It's pretty cool to see the image. So I don't know, like I know that you put a lot of hard work in it, but I don't know how exactly we make it. it's like really nice. So I just
How the riser is made?
yeah.
Yeah, so for the riser pipe, we need to select different vendors for high quality to produce a high quality steel if it's a steel riser. And if it's a flexible riser, there are currently very limited vendors which can produce flexible risers with track records. There are, I would say, we can count maybe 2 or 3 vendors which can produce the flexible pipes. And for the riser pipe, there are these different vendors, but there are connections of the riser pipe to the vessel, so including different. We call it titanium or steel stress joint to connect to the vessel, or use a flex joint connection to the vessel. There are also different vendors for those connections. And also if you use a high strength material, and then the connection was threaded and coupled connectors. There are other vendors for that. So putting all these together, then we will need either weld connection or like threaded coupled connection, and install it offshore. Install. So there is another installation contract goes into it to install the whole system. Like the amount of values goes into all this, it's like hundreds of millions of dollars goes into the whole process. Did I answer the question? So
Thank you so much.
yeah. Any other questions? This
Looks like Jason has a question, has his hand.
oh, Jason. Yeah. Hi, Jason.
So how do you get the pipe underwater without having water get into it?
Oh, okay. Yeah. So there are different types of risers. So like there are water injection risers, which we will inject water in it. But for the production risers, will directly connect the pipeline to the reservoir itself. So the what produced from the reservoir will go through the pipeline because it's under the seabed. So it's directly connected to under the seabed. The production fluid will transfer from the pipeline, and the pipeline is lying on the seabed and connected to the riser. So it's like the production fluid is like directly coming from the reservoir instead of coming from the seawater. That's how it's producing production fluid instead of not in the water. Of course, there was some water content from the production fluid. So normally there would be, you would need to analyze the content of the production fluid. There would be a certain percentage from the production fluid. And there will be certain percentage of oil and certain percentage of gas. Yes. So, any other questions?
All right. It looks like we're a little bit over time, and if there are no more questions, maybe we'll give.
Actually, when the pipe goes down, does it eject air so water doesn't get in?
Does it what? Can you repeat your question again, Jason?
Eject air so the water won't get in.
Oh, so there are different function of the riser. So for example, if there are gas injection riser, it's injecting gas in the inside the riser. Or if it's water injection, there will be injecting water. But for the production, mostly it's not used for injecting things inside. So what is coming out of the reservoir is directly inside the production pipe, production riser. So there will be certain amount with water. So it's not like no water at all. There are water content in the production fluid. It's not like a 0% water. There will be some content.
Thank you.
Thank you, Jason.
So what was
Again, yeah, did
the Chinese college entry exams like? You know, the Gaokao exams.
Hello?
Jonathan, did you have a question?
Yes, can you hear me?
Yes.
So what was taking the college exams like? Like, were they hard?
What a college exam? Like how I took the college exam in China?
Yeah, the Chinese college.
Oh, yeah, that was extremely difficult, I would say, if you want to get a good score. So it's not easy to get into, I would say, top college, top university in China. And it's because so many students and the population in China is huge. Millions of students taking the college entrance exam, and there are limited top universities in China. So after you get the score of the college entrance exam, you in our days we don't get the score directly before we enter, like fill in forms to apply for university. So maybe at that time you have to estimate how much score you get. So we will do some estimation. You will get the answer sheet, I remember, yeah, and then estimate what your score will be. But you, without knowing other people, other people may get different scores, although you think you did well, but you don't know how relative well you are doing in your exam. So based on that estimation, you have to apply for different schools. If you have confidence, then you can apply for the top university. If you don't have that much confidence, then you apply for lower grade universities. And it's not like you can apply large amount of universities, because lots of good universities don't accept if your wish list is ranked the second. Like if you don't apply the top university as your first wish application, the top university usually won't accept for that. So kind of also risky. You have to take the risk, and you have to be confident with what you get. It's lots of competitions, you know, during that time.
Thank you, Dr. Yin. Jonathan, I hope that addressed your question. Aaron has another question. Will surface pressure break the underwater risers in the oceans?
Yeah, surface pressure is also very key. Like could result in high stress in the riser. So normally in the strength analysis we conduct, we need to take into the pressure into account. So the high pressure system will have a end cap effect, which may burst the riser system. So you have to check that the burst capacity is met, and if the pressure has variation, if it varies during the surface, so the pressure cycles may cause resulting in fatigue damage as well. If that is the case, then the pressure cycles also needs to be taken into account in the fatigue calculation. So it is a very important, a key input in our analysis.
Thank you, Dr. Yin. I know we're 10 minutes over, so we certainly appreciate you spending the extra time with us this morning. I mean, everyone is so impressed with the presentation and so curious about the work that you do. So thank you for sharing all of those insights. And obviously, there's a lot of, you've learned the engineering expertise that you have is just mind-boggling. I was just thinking about, if I get furniture and just to put furniture together with instructions is very hard for me. This is, you're building something in a very dynamic environment, and primarily through simulations, and then, on an ongoing basis, testing and taking that feedback and adjusting for it is amazing. And I think a lot of folks are appreciating your presentation. Hopefully you're able to see that on chat. Just to conclude, again, it's the challenge is to build something in a very, very dynamic environment, as you can think about building something within, in deep sea. And primarily, so that's the problem statement. And it's mostly the design is done through simulations, and also through Jason's beautiful question, we all learned that it's also, there's some prototyping that gets done, right? And, in order to maintain the structure as well as extend the life, there is inspection and there is feedback mechanism that comes, right? And to be able to extend the life, which is wonderful. And then we also learned about sensors that are utilized for that as well. And, one of the things that I found interesting was, as Dr. Yin was talking about inspection, there are tens and thousands of parameters that they might measure, but it's important to prioritize, right? So in general, I think we should all think about prioritization. We cannot solve all of the problems, but what are the most critical problems to solve for, so that you can address the problem in the most efficient way. Yeah, I know we have taken more time today, but this was so interesting. So I think everyone was super engaged. So with that, we will let you have the rest of your Saturday. And again, Dr. Yin, thank you so much for your time today. This was excellent. It was great to learn everything about everything that you do. That's wonderful. Thanks.
Thank you.
Thank
everyone.
you.
Thank you. 谢谢。
Don't forget to subscribe and like. If you have any questions, you can email info@agoramasterco.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!